Hello, this is a physics video on entropy. Now for 10 years, actually, I've been making videos from Young and Freedman's University Physics. And with this video, this is the second to last video in the section of the book on thermodynamics. We've been through, in about 700 pages, the equivalent of 2 physics courses. We did a course, as it were, on mechanics and dynamics, and we're about to finish, we have one more video, a section on thermodynamics, and then at long last we will start electromagnetism, which I'm really excited about. In fact, that was my first real interest in physics back in high school, the 9th grade. I took a course in electricity and electronics. Anyway, that's not important. Who cares? This video is on entropy, and this is chapter 20. We're almost done with chapter 20 on the second law of thermodynamics. And the second law of thermodynamics basically says that everything gets more random. Things don't get more ordered on the whole. We're losing heat in the universe, and eventually it'll all go cold. But anyway, things go from ordered to disordered. If I put drops into a beaker, drops of colored liquid, it will spread out. It's never going to randomly get back to the original drops. It's not going to happen. If I shatter something, it's not going to on its own go back together. Second law of thermodynamics. However, most of what we've talked about so far in the chapter has been kind of qualitative discussion. Now we want to put math to it. I mean, there's been math in the chapter, sure. But entropy is a quantitative measure of disorder. And the guy that coined the word entropy was Rudolf Clausius. And I believe what we're about to see here is the way that he came to mathematically define entropy. So as it turns out, the disorderedness of a system is what we call a state function. Internal energy is a state function. In theory, we could add up all the internal energies of all the molecules in a system and come up with an internal energy. That's impractical, right? Because I'm a big person and these are very, very small. And so it's more practical to talk about, say, the difference in internal energy than to calculate the internal energy at a particular state. As it turns out, entropy is also a state function. That is, there is a certain amount of disorderedness, we can say, in a system at a particular point. And it doesn't depend on how you get to that point. At that point, that's the quantity of disorderedness. However, because of the microscopic nature of the world, it's impractical to add up the entropy of something. And so, once again, the change in entropy is going to be more valuable than the actual entropy at a particular point in time. Well, Clausius, being a clever guy, basically said, okay, in a way, it doesn't matter exactly how we define entropy, as long as we define it and we're consistent with everything else from there on. And so he basically reasoned this way. When you have the expansion of something, let's say you add some heat, but you keep it at the same temperature. So consider an isothermal expansion of an ideal gas. So it's expanding, but it's staying at the same temperature. So we don't have an increase in internal energy, right? Because the amount of internal energy depends only on the state it's at. And so we are going to consider an isothermal expansion of an ideal gas because of added heat. So since there's no change in internal energy, U equals Q plus W, right? Internal energy equals heat plus work. So if the internal energy is 0, the change in internal energy is 0, then the infinitesimal change in heat is going to equal the infinitesimal change in work. Well, we know from earlier in the chapter that work equals PdV, or that dW equals PdV, that the infinitesimal change in work equals the pressure times the infinitesimal change in volume. And so what is P? Well, PV equals nRT. So P, if I divide by V, then I've got P equals nRT over V, dV. All right, now we're talking, right? So if we take the first and the last of these two, dq, let's go and divide by nRT, dq over nRT, and we already had dV over V. All right, so we've got this relationship that in an isothermal expansion of an ideal gas because of added heat, we've got this relationship. Okay, now here's what Clausius reasoned, that there is an increase in entropy. There's an increase in entropy when we have this infinitesimal change of volume over a total volume. And that change in entropy is proportional to dq over t. These are nr as constants. So dq and t are the variables, as it were. And so here's what Clausius says to himself. Hey, Clausius, why don't I just define entropy, the infinitesimal change in infantry, not infantry, that's a military thing, the infinitesimal change in entropy as the infinitesimal change in heat divided by temperature. And voila, we have a way to quantify entropy. We could have maybe done it a different way. I mean, we could have done it with 2 dV over V, you know, or whatever. But basically, we have found a way to quantify entropy. And as long as from this point on we're consistent, yay, we've done it. We've come up with a way of quantifying it. So the entropy at any particular point is the entropy at that point, state 2, or entropy 2, S stands for entropy, at the second state of entropy minus the first state of entropy equals Q over T, the amount of heat at that point divided by the temperature at that point. Okay, so there we have it. Now, because this is an isothermal expansion and it is a reversible process, and so this is the formula for the amount of entropy in a reversible process. Now, we can also then put it as an integral, that the change in entropy is going to be the integral from state 1 to state 2 of dq over t, right? And there we have it. We've got a nice little formula to calculate the entropy at point 2 when it has come from point 1 by way of a reversible process. Okay, so got some math now. We've got a mathematical basis for entropy. Well, let's talk about the implications of. I've already told you some of these things, I think, but here's some of the consequences. So one of them I've already mentioned. Entropy is a state function. It doesn't matter what path it takes to get from state 1 to state 2. The entropy at state 2 is going to be the same either way. Let's say you came from here, or you came from here, you came from here, you came from here to get to state 2. Doesn't matter. I don't care how you get there. Just get there if you can. You know, whatever the state you end up with is going to have the same amount of entropy no matter what path you take to get there. So entropy, as I said, has a definite value for a system, but it's not practical to add up the entropy of a particular system. It's much easier to talk about the difference in entropy. Now here's a trick. Man, these physicists are darn clever. Let's say I want to know the change in entropy from state 1 to state 2, but I used an irreversible process. Now, I can't use the formula. The formula was the integral from 1 to 2, you know, of dq over t. You know, that was created for reversible processes. I can't use that formula if I got from state 1 to state 2 by a irreversible process, a process that can't be reversed. But here's the trick. What if I imagine a process that would get you from state 1 to state 2 via a reversible process? Then I can use the formula. The change is going to be the same anyway, right? Because the state is the state. It's a state function. So by imagining, okay, I want to figure out what the change in entropy was from state 1 to state 2 via this irreversible process. So I imagine a situation in which I get from state 1 to state 2 by a reversible process, and that'll be the same change in entropy because it's a state function. All right, a definition slipped in this section is isentropic. An isentropic process is one that is a constant entropy process. So for example, if you have a reversible adiabatic process, that would be an example of an isentropic process. And as we have said previously, an adiabatic process is one in which no heat is added to the system. There's no change in heat in that process. All right, so let's talk about entropy in cyclic processes. So like a Carnot cycle. The total entropy change during any reversible cycle is 0. Now, as we'll see at the very last of this video, you can never have a decrease in entropy for a system. Most of the time, there's going to be an entropy increase because of a process. However, it is possible to have a cyclic process in which a cycle is reversible and there is 0 entropy change. That is to say that the integral of the infinitesimal change in heat, dq over t, is 0. So let's think about this a little bit. You might remember from earlier in the chapter that well, here, this is early in the chapter. The Q at the cold, the amount of heat at the cold, the amount of heat lost at the cold over the amount of heat at the hot equals the negative of the temperature at the cold divided by the temperature at the hot. All right. So we do a little bit of arranging, and so we let's see, how do we do this? We're trying to get to TH over QH. So basically we multiplied both sides by QH, and then we divided both sides by TC, and then we brought the negative onto the same side, and voila, we've got this equation over here, QH over TH plus QC over TC equals 0. But we've defined Q over T as delta S, right? So at this hot temperature, the change in entropy, this equals the change in entropy hot, and this equals the change in entropy cold. And so basically, the change in entropy at the hot point is going to equal, because it's negative, the change of entropy at the cold part. And so we have a total change of entropy of 0. Well, let me go ahead and break this down. There, that looks better, doesn't it? We'll unfold it like a mystery novel. Okay, so basically, because the delta S at the hot and the delta S at the cold is 0, it evens out. And so in the case of a cyclic reversible process, the change in entropy is 0. Now, we started off thinking of that in terms of a Carnot engine with an ideal gas, but it applies basically to any Carnot engine, because he justifies it if you turn to page 695 in my hymnal. But basically, because of the efficiencies working out the same, it doesn't matter whether it's an ideal gas or not. It's the same for any working substance. And then he goes on basically to show that it doesn't have to be a Carnot cycle. As long as it's a reversible cycle, this is going to be true for any reversible cycle. So again, to generalize that, in the case of any cyclical reversible process, the change in entropy can be 0. However, if it's an irreversible process, there will always be an increase in entropy. So we have two possible conditions here, and I'll quote him. When all systems taking part in a process are included, the entropy either remains constant, that is, the change in entropy 0, or it increases. You cannot have a decrease in entropy in a system. Simply cannot happen. No process is possible in which the total entropy decreases. Well, got through this video. This has been a video on entropy in Young and Freedman's University Physics, Chapter 20, the second law of thermodynamics.